Como dice Marie Curie, en la vida no existe nada que temer, solo cosas que comprender. Recuerden correr y buscar la manera de aprender que más les divierta. Neil deGrasse Tyson dice: nadie que es curioso es tonto. Las personas que no hacen preguntas permanecen ignorantes el resto de su vida. Y para ustedes, esto es curiosidad científica. Buenas, corillo de curiosidad científica. Bienvenidos nuevamente a este su programa de curiosidad. Y el día de hoy, este podcast va a ser en inglés, porque mi invitado del día de hoy, que es una persona súper especial, él es un físico de partículas y él sabe mucho más que yo sobre estos temas. Así que démosle la bienvenida. You know, like the biggest, happiest welcome to my friend Daniel Whiteson. How are you, Daniel?
I'm good. Thank you very much for having me back. And apologies that we can't have this conversation in español. My Spanish is not good enough.
That's okay, man. That's okay. You're not the first one talking English in this podcast, so I know they enjoy it anyway. So today, I'm pretty happy. For you guys that didn't listen to my first conversation, like almost like a year and a half ago or something like that, I think, or like a year ago. Daniel Whiteson have his own podcast that is called Daniel and Jorge Explain the Universe. And also, they know each other because they create like one of the better, biggest books to explain how science works. That is called We Have No Idea, A Guide to the Unknown Universe. So for all of you guys that want to introduce yourself to science and physics and a little bit of particle physics, I think that's a great book to start. So Daniel, if you want to tell us a little bit about your book before I jump to a thing that is blowing my mind about particles. But first of all, what we can find in your book.
Sure, thanks very much. Yeah, we have a podcast, Daniel and Jorge Explain the Universe, where we talk about all the big mysteries of the universe, all the biggest, deepest questions. And our book, We Have No Idea, is sort of where that started. It's all about the things that we don't know about the universe. What is space? What is mass? Because we like to encourage everybody to be a scientist, and that means bringing everybody up to the sort of level of ignorance of current science. We want to admit all the things we don't know, and that helps get people oriented so that when we do discover the basic secrets of the universe, soon, I hope, they'll understand the questions we were asking. And we actually have a new book coming out this fall. It's called Frequently Asked Questions About the Universe, and it comes from our podcast. So the most commonly asked questions we get on the podcast: what's it like to fall into a black hole? Why can't I travel through time? Where did the universe come from? Explained using very simple, easy to understand terms, and of course Jorge's awesome cartoons.
That's great. That's great. Yeah, because this book have a lot of pictures, so it's kind of easier to understand because you can see when you see things, it's way easier to understand. But,
yeah, and our attitude is that science doesn't have to be hard to understand. We're not trying to intimidate people. We want to make people feel like they can understand it because they can, because a lot of these things are questions everybody has. People want to know, how does the universe work? It's not just for a few scientists sitting in a laboratory.
Yeah, that's exactly right. That's why I created this podcast that is called Scientific Curiosity, just because of that, because there's so much stuff that... and one thing that is impressive to me is that when I was a nerd since I was young. I read a lot of science fiction. So I kind of fall in love into science because science fiction. And then, you know, I start reading more books about science directly and things like that. But when I actually start this project, like the podcast, I have a lot of questions, like why the sky is blue and why, you know, why we see colors and things like that. And then suddenly when you start reading, it's like, oh, we already have the answers to all of this. So it's pretty curious to you know, to learn about this stuff. And talking about curious things, it has been in the news lately, something about certain particles that I think that at some point we think that we understood what it was going on or happening, or calculations, we thought that they were okay. But recent news says that there is a particle that is called a muon, that is not acting the way we were supposed to, to see it. But before that, maybe if you can enlighten us about how do we know this particle and what it is.
Yeah, that's a great question. We are not sure why the muon exists. The muon is just like the electron, but it has more mass. So it's like if you had a cousin who's heavier, but like 100 times heavier than you. And you might ask, like, why does it exist? It doesn't appear in atoms. When you look inside hydrogen or helium, you don't find any muons. It's all quarks and electrons. So why does the muon exist? We don't know. But it turns out that every particle out there has one of these cousins. The electron has a cousin. In fact, it has two cousins. There's the muon, and then there's another one called the tau. And the quarks, they also have these cousins, like the up quark, which is the one that you find inside the neutron and the proton. It has cousins, the charm quark and the top quark, that are also heavier. So this is one of the sort of well-known things about physics that nobody understands. Like, why does every particle have two cousins? And so the muon is an example of this. It was discovered almost 100 years ago in cosmic rays. It means that muons are created in the atmosphere when particles from the sun or from other galaxies hit the atmosphere. They make these basically little particle explosions that create muons. And the muons rain down on the Earth. And so muons are everywhere. There's like 1 muon per square centimeter per second passing through you all the time. They're not rare. So it's just like a rain of muons that you mostly don't even notice. And so muons are interesting and they're weird. Nobody knows why they exist, but they're also useful to help us try to find other weird particles. And that's what this experiment is about, is using the muon as a way to discover if there are more weird particles out there that we didn't know existed.
Oh, okay. So you just said that the muon is like a cousin of the electron. And like you said, they're not part of the matter, like the matter that we all, see or whatever. So
right.
Do we have any application for it? Like for example, can we use the muons like to put it in a laser beam? So it will, you know how the lasers are supposed to work, that you have electrons there and then they suck the energy out of the photon and then just shoot it back like a bigger, I don't know, something like that.
No, that's a great question. I don't think I've ever thought about that. Are muons useful for anything? Muons also don't last very long. If you have a muon, it lasts for microseconds before it decays into an electron. Because the universe doesn't like having a lot of energy in one place. It likes to spread energy around. So when you have a lot of energy in one place, like a muon, and it can decay into a lower particle, it likes to give up that energy, explode into an electron and a couple of neutrinos. So even if you had like a big pile of muons, you spent a lot of money to make muons, they would only last for a few microseconds. And so they're pretty hard to do anything useful with. I don't know anybody who's done anything practical with muons. That's a cool question. Yeah.
Okay, yeah. So we understand that they don't last too long. Most of the things that are heavier, talking about particles in the universe don't like that, or don't like things that are too charged. Because even in periodic elements, things that are too charged, they tend to decay. But talking
it's sort
about
of like things rolling downhill. A boulder doesn't like to sit at the top of a mountain for very long. Eventually, it'll roll down to the valley. And that's the way it is with everything. You don't like to have a lot of energy concentrated in one place. Things like to relax and spread out.
Okay, yeah. So then about that, because we do know like the muon have like a charge, right? It's the same as in the electron, like a negative charge.
Exactly. The muon and the electron and the tau all have all the same quantum properties: spin, charge, all of that stuff. Exactly.
Okay, so then if we're talking about the spin and all that, I don't know if this is correct, but we use magnets, right, to like control or manipulate the muons, so we can, make them roll inside the LHC. Or
yeah,
how do we do that?
We can use magnets to control these particles, because magnets bend the path of charged particles, right? This is a very basic thing about magnetism. You have a magnetic field line and you have a particle coming perpendicular to it. The particle will bend around it. That's why our magnetic field protects us from particles from space. Huge high energy particles that would otherwise hit the atmosphere get bent around magnetic field lines of the Earth, and they get funneled around those lines up to the North Pole or the South Pole. So magnetic fields bend the path of charged particles. That's why we have, for example, the northern lights and the southern lights. Those are charged particles from space that got pushed up to the North Pole or the South Pole because particles like to move along magnetic field lines, not perpendicular to them. And so we do the same thing at particle accelerators. We can take particles and we can bend them into a circle. That's what we do at the Large Hadron Collider. We have protons, and because they're also charged, we can use magnets to bend their path. And that way we can get them to move in a circle, which allows us to get them to go really, really fast. But it's sort of weird why particles have their own magnetic field. Like, it's true that particles have a charge, so you can bend their path, but they also have little magnetic fields of their own, which is pretty weird.
Yeah, that's exactly where I wanted to go. Because pretty much what the news says is like the scientists didn't realize like the muon have like a like more magnetic moment or something like that. I really don't understand what they mean by that, because I know that we manipulate them with magnets, but I didn't know that part. I didn't know that actually the particles have their own magnetic, field or moment. How is that?
Yeah, it's kind of mind-bending to think about, because where does a magnetism come from? Well, if you want to make something magnetic, you can take something that has electric charge and move it in a circle. That's how, like, for example, electromagnets work, right? You take a current, electric current, you spin in a circle, you get a magnet. Cool. Well, how does it work for a particle? Well, particles have a charge, all right, so that's one ingredient. They also have this thing called spin. They have a quantum spin. And a lot of times people imagine that means that a particle is spinning like a top, like it's a physical thing that's turning. And that's not exactly what's happening, because particles don't have a size. They're zero volume. There's like no length or width or height to them. They're a point. So a point can't spin, right? Because there's nothing to spin. But somehow, weirdly, they have this other property. We call it quantum spin because it's similar to spin, but it's not actually physically spinning. But the weird thing about quantum spin is that it behaves just like spin, because if you have charge and you have quantum spin, you get your own little magnetic field. So every electron and every muon and every quantum particle that has charge has a tiny little magnetic field, a little north and a little south. And so that's where the magnetic field comes from of these particles. It's a little quantum property.
Wow, that's pretty weird, because now my brain hurts more than before I bring you.
Yeah, it's weird. Once you start opening these things up, you start asking yourself questions, you realize almost none of it actually makes sense. But you said earlier something which was very important, which is that the magnetic field of the muon is not exactly what we expect. And you're right. And the reason is that the muon is not just by itself. Like a muon by itself would spin and it would make a magnetic field because it's spinning and because it has a charge. But remember that magnetic fields are connected to electric fields. We don't just have the magnetic theory and the electric theory, we have the theory of electromagnetism that tells us magnetic fields and electric fields are really two sides of the same coin. And that makes sense, because here we get a magnetic field from a charged particle, an electrically charged particle. So what that means is that there are photons everywhere. The muon is never by itself. It's constantly surrounded by little photons, because that's what an electromagnetic field is. It's just a bunch of photons. Like every time you feel a push or a pull from a magnet, that's because little photons are wiggling back and forth to say, hey, this should be pushed, or hey, this should be pulled. Every time you feel a push or a pull from electricity, those are photons. Every time you see electricity, lightning, those are photons. So photons are sort of like the basic building block of electromagnetism, and that includes magnets. And so a muon, because it has a charge and it's spinning, makes a magnetic field, but it also basically has a swarm of photons moving around it. And those photons, and what those photons are doing, how they interact with everything else, determines also that muon's magnetic field. And that's where this experiment comes in. They try to measure the muon's magnetic field very, very precisely, because it tells them what those crazy photons are doing that surround the muon. It's like a little cloud of the little cloud of photons around the muon, and we're interested in what those photons are up to.
Okay, yeah. So to put it like in words that, and you can correct me if I'm wrong, but it kind of makes sense that if you have a particle that is so charged, usually if it works like electrons, electrons get like their energy or charge from photons and then they release them. So it would be kind of like that, like these muons have this charge or whatever, because they probably like attract that light, attract that photon. That, by the way, the photons is pretty much like the particle that move the particle that actually carry the force of the electromagnetic force, right?
Exactly, yes.
Okay.
Exactly. Every time electromagnetic fields are created, those are photons. Every time they change, those are photons. If you make a magnetic field and you wiggle it, that's a photon. Basically, it's all photons.
Okay.
And it's really interesting because we want to know what particles are out there, like what kinds of particles exist on nature's menu. Like we were talking about before, there's the electron, there's the muon, there's the tau. We don't know why those three particles are there, but seeing that pattern starts to let us ask the questions like, why do these exist? Do other particles have cousins? Why three and not four? We don't know the answer. And we're hoping to get an answer by seeing the bigger picture. Like maybe there are more particles to the puzzle. And if we saw more of them, we would understand the pattern. You know, maybe we're just like looking at a tiny little piece of the puzzle. If we zoomed out and saw the whole picture, it would be, oh, that makes perfect sense. Like if we only looked at 4 elements of the periodic table, it would seem confusing. When you see the whole thing, you're like, oh yeah, it all clicks together. So we're hoping to figure out what other particles are out there. And one way to do that is to use the Large Hadron Collider to smash particles together at high energies and make them. But another really clever way to do that is to see what photons are up to when they're swarming around muons, because photons basically get up to crazy stuff. Photons, when they're swarming around the muon, this cloud of photons around the muon can basically turn into any kind of particle that's out there. And when they do that, they change the muon's magnetic field a little bit, and we can measure that. So by measuring the magnetic field of the muon really, really precisely, we can get a measurement for what that swarm of photons is up to, and if it made any new weird particles we weren't aware of. That's the basic idea of this whole experiment.
Oh, okay. So if I'm understanding right, I could say that maybe this is a crazy idea, but maybe it's like the photons are working, around the muon, and they're creating like their own kind of dynamo, maybe that then create that kind of electricity that, of course, create the magnetic moment. Oh my God, that's so cool.
I know, it's crazy, and this is happening to every muon, every electron, all day long, all the time. There's just like so much going on constantly in the world around you. You're looking at like a brick or a rock, it's like filled with crazy energy and particles swarming and buzzing and doing all these things all the time. The universe never sleeps.
Oh, something that is crazy is that you just said like there are kind of points in the space, all particles pretty much, but like talking still about the electron and muon and tau, they really don't have like a, they don't really cover space, but they are in there for some reason. But I have read before that we cannot really measure the volume of that, like how many particles or electrons we can put in a certain point, let's say like in an atom nucleus. So we cannot measure actually the size of it. So when we talk about a particle that is, like a cousin, like in this case, the electron, how do we know that it's more massive? Is you cannot really say like, okay, they're all, like we can only fit 20 muons in this bottle and we can fit 50 muons in this other bottle. Like when we talk about mass, it's not literally mass like physical space volume. It's something else.
That's right. And we're not talking about mass like physical space volume, because these particles are not made out of some sort of like basic particle stuff. It's not like the muon is a bigger scoop of universe material than the electron. They are the same size. They are exactly the same size, and they are both zero size. right? They're point particles. And so immediately you're like, hold on, wait, you just said it has stuff to it, but now you're saying it's zero volume. That makes no sense. You are exactly correct. That makes no sense. And yet that is our best understanding, that these things are point particles and that they have mass. And the confusion comes from thinking about mass as connected to volume. Like you were saying, you measure the mass of the muon by seeing how many you can fit into a bottle. That's measuring the volume of the muon, right? And you think, oh, well, there must be a connection because, mass takes volume. But does it have to? Like, you don't think about whether there's enough room on a particle for its electric field. Like, where does the charge of a muon come from, or the charge of an electron? If something has more charge, you don't think of it as being bigger. So you should think about mass the way you think about electric charge. It's like a label we put on a particle. We don't know where it comes from necessarily. We can talk about that, though that might require a whole other podcast. But it's just like a property of the particle. Some of them have more, some of them have less. It doesn't mean that they're bigger or that they have more stuff to them. It just means that they have more mass. And we can measure that because we can see how they move. Things with mass move differently than things without mass. Like, it takes more energy to get them up to a high speed, right? Force is equal to mass times acceleration. So you apply a constant force to an electron and the same force to a muon, the electron accelerates more because it has smaller mass. And so that's how we can measure the mass of these particles, even though, we don't really quite understand how they can have mass without volume. We know, and we can talk about that if you like, that the mass comes from their interactions with Higgs bosons. But again, that's probably another hour-long discussion if you want to go there.
Yeah, but we can maybe give a short version that I can maybe say it, and you can correct me if I say something crazy. Sure. But to me, like, when people talk about the Higgs boson, it's like this particle that have interactions with other certain particles, not all of them too. So that's another crazy thing. But the thing is, like, imagine like if you're in a party and I'm with Daniel Whiteson, the greatest and best guy ever, and we're hanging out in this party, but they don't know who I am. They don't know Augustine. So I can probably come from the entrance to the bar easiest. And then Daniel, everybody knows who's the great Daniel Whiteson. So everybody's going to start talking to him like, hey, man, how's your new book? Hey, man, how's your new book? Hey, man, how's the podcast? That's the difference. Like, we both are like 180 pounds, but for some reason, people want to talk more with Daniel than me. It's kind of like that.
Well, that's kind of a ridiculous example, but yeah. Particles move through the Higgs field, and some of them interact with the Higgs field a lot, and that changes the way they move. It changes the way they move as if they had mass. So another way to think about it is, do particles actually have mass? They don't really, but they have another kind of charge, and this charge makes them interact with the Higgs field, which means they move as if they did have mass. And so some particles move as if they had a lot of mass, and some particles move as if they had a little bit of mass, and some don't interact with the Higgs field at all, and so they move like massless particles. So the whole concept of mass is very confusing. It's actually one of the chapters in our book. What is mass? For tiny little particles, mass is this weird quantum property that doesn't really align with our like intuitive understanding of what mass is like having stuff. It's just this weird property that means you accelerate differently than if you didn't have mass. And then when you put stuff together, right, like the proton, it has a lot of mass. Its mass doesn't come from the quarks that make it up. If you put those quarks together and you tie them together with a bunch of energy, that energy also creates mass for the proton. So mass is a very, very weird thing. Most of the mass of what you're made out of isn't the mass of the particles that make you up, the quarks and the electrons. It's mostly the energy of the bonds of those particles held together is what makes your mass. Anyway, the muon has mass like other things, and it has a different mass from the electron and a different mass from the tau. And that's another one of the deep mysteries of particle physics is, why does the muon have this larger mass, right? Like, we have these cousins. The muon is a heavy version of the electron. The tau is even heavier. There's no pattern there that we can see. It's not like the same pattern appears for the other cousins, like the up, the charm, and the top, and the same kind of cousin relationship, but their mass ratios totally different. And there's another set of cousins, the down, the strange, and the bottom quarks, similar sort of structure, totally different mass ratios. So we have no idea why some particles have a lot and why some particles have a little. Mm-hmm. And the discovery of the Higgs boson tells us sort of how particles get mass, but it doesn't tell us the deeper answer to the question, which is why do some have a lot and some have none and some have very little? We're totally clueless about that.
Wow, it's incredible because another thing is like we only use pretty much like 3 particles, like quarks up, quark down, and electron, and that's all the matter that we know. Like we don't even have an idea why we have so much particles at all.
Yeah, well, all the other ones are unstable. What we use are the lightest ones, the ones that everything ends up in. If you create a top quark, eventually it will decay into up quarks, down quarks, and electrons, because that's where everything goes. It's like the lowest rung on the ladder. And everything eventually shakes down to those lowest rungs. So that's why stable matter that you and I are made out of, are made out of these. But it's really interesting to see what are the other rungs in the ladder. How far up did the ladder go? We don't know. Are these particles that we found, these 12 particles that make up matter, are these all of them? Are there 12,000? Like, does the ladder continue up forever? We have no idea. Like, we're so ignorant. We've seen such a tiny little fraction of the universe. But you're right. We're made of these 3 particles, the lowest rungs on the ladder.
Well, yeah, I'm guessing it's because of that, because you just said that they are more stable, pretty much. But then going back to the muon, so pretty much at the beginning when they started making the test, how were they thinking about like, okay, this is supposed to have this, magnetic moment? What happened, or what did they, what was the expectations for them? Like, it is supposed to move this way, but what did they found that didn't match their idea?
Yeah, this is like a decades-long story. It's really interesting. They did this experiment at Brookhaven National Lab about 20-something years ago. And what they did is measure really precisely the magnetic moment of the muon. That means how the muon responds to magnetic fields. And we said before that muons don't last very long. So it's hard to do an experiment on something that only lasts for microseconds. So what you do is you got to get the muons moving really, really fast, because then their clocks are slowed down by special relativity. Like if you have somebody on a spaceship and they're going at nearly the speed of light, and you looked at a telescope into the window on their ship, you would see their clock moving slowly. Same thing for a muon. You take a muon and you get it going really fast. What happens? Its clock runs slowly. So it says, well, I'm only supposed to be around for a few microseconds, but 10 minutes later, it thinks half a microsecond has passed. And so in your time, you can have muons that exist for tens of minutes or hours or even longer, because you're slowing down their clocks with special relativity. So they pass them around in a circle. They use a big magnet, pass them around a circle going really, really fast, and they measure the direction of their magnet. And does their magnet change as they go around the circle? And that tells them exactly how their little magnetic field works. But that's complicated. And in order to know whether you've learned something, you also have to know what to expect. Like you were saying, you have to know what the magnetic field should be. So there's really 2 parts of this story. One is like, build a machine that can hold muons, spin them around, and measure their magnetic field very precisely. The other part is to calculate exactly what we expect, because we expect the muon to have a bit of a weird magnetic field. It has all these photons, this cloud of photons around it. And these photons can do things. Like a photon doesn't just hang out. Photons, they zip around at the speed of light, but also they like to do stuff. Like a photon can sometimes turn into other particles. It will turn into a positron, an anti-electron, and an electron, very briefly, and then go back to being a photon. Or it'll turn into a pair of quarks very briefly, or it'll turn into a pair of muons or something else. In fact, a photon can turn into any particle that has electric charge. And so what we try to do is calculate, like, well, what can photons do and how often do they do it? Because everything that a photon can do, every time it can turn into these other particles, changes the magnetic field a little bit. And so we need to calculate that very precisely. And so to do this, these theorists, they write down these little diagrams that describe like what a photon can do. And there's thousands and thousands and thousands of these diagrams. It's a really big job to consider all the possible things, because like a photon can turn into an electron and a positron. That electron can then give off a photon, which then turns into more particles. And like it just goes on and on and on. And the more steps there are, the less likely it is. But if you want a really precise measurement, you want to like really hunt down if anything weird is going on, you want to do it very accurately. So this is like one of the most precisely measured and predicted quantities in all of science. They have it down to like 10 decimal places, exactly how strong the magnetic field of the muon should be. And it's a huge amount of work to get it right. So they did this experiment like 20 years ago, and they got the two numbers, the measurement of the magnetic field of the muon and the prediction for what it should be based on all the crazy things a photon could do. And they didn't agree. They were different. Wow. They're like, ooh, that's interesting. Because immediately that thinks, well, either you made a mistake or there's a new particle in there. Because if the photon, if there's some new particle, call it a squigglion, if the photon sometimes turns into a squigglion and you didn't include that in your calculation, then you're going to get the wrong answer. So getting the wrong answer might mean that there's a squigglion in there that the photon is turning into in the experiment that didn't exist in your calculation, and that's why you're seeing a discrepancy.
Wow. So right now, I think I have like two more questions about that. Because so since the photon can turn into another particle, and then when it turns, it's changing or affecting this muon magnetic field or magnetic moment. It could be like a new particle, like anything, like particle from force, like a new force, or particle for like another just matter particle or whatever that we don't use or whatever.
Yeah, it could be anything. For example, photons sometimes turn into W bosons, which are the force particles of the weak force, because W bosons have electric charge. Photons can only turn into particles that have electric charge. They turn into the particle and its antiparticle, like electron and positron. They can't turn into neutrinos, for example, because they don't have electric charge.
They are neutral.
Yeah. So any particle that has electric charge, the photons can turn into the particle and its antiparticle. And that includes new forces. And there could be new forces out there that we are not aware of that have force carrying particles that have electric charge, and the photon could be turning into them. So that's why it was very exciting like 20 years ago when they saw this discrepancy. They said, ooh, this is interesting. Maybe this means that there's some new particle out there. Now, the power of this method is it's really broad. Like it's basically asking the universe, did we miss anything? And the universe says yes or no. Problem is, it doesn't tell you what you missed, right?
Yeah.
It's like, measuring the weight of a whole house and then predicting its weight. And you say, well, I got it wrong. Something in my calculation is wrong. What is it? Is the couch too heavy? Like it doesn't tell you what you missed. It's very indirect. So it's a good clue. It's like saying, keep looking. There might be something there, but it doesn't tell you exactly what it is.
Yeah. Wow, that's crazy. It's that another thing that I didn't knew. Like I don't know if my, like the people that listen to me knew this, but I didn't knew that photons can only turn into particles that have charge. So it's crazy because the photons don't have charge. So
that's right.
That doesn't make a lot of sense to me. But
yeah, it's weird because they only interact with other particles that have charge, but they don't, which means photons don't interact with each other. Like you shoot two photons at each other, they will pass right through each other as if they don't exist. So technically a lightsaber should never work because photons don't bounce off of photons.
And anyway, you cannot like keep like electricity or whatever light just standing there.
Lots of other reasons why photons don't, why lightsabers aren't real, but
yeah,
so, exactly.
Okay, then what are we expecting about these results? Like we already like, or at least we think that it could be like a new particle. It could be some new force because like a particle that carry the force. And what if that particle, what is going to be like the next step to recognize? Because there is like you said, it's not the same when you don't know if it's the couch or whatever in the house to measure that weight.
Yeah.
But to me, like we have a calculation about that we were missing something, and then we thought about the Higgs boson. So we kind of, we were kind of looking for it. But at this point, we were not really like pointing this thing to nothing. You know, we don't have a new Higgs whatever. So what, you know, do you guys, or that, you know, like these scientists are creating new theories, new calculations to either put in a new particle that maybe have like a different, you know, like contact or with particles, or maybe like the Higgs boson that give mass to certain particle, then it's this new particle that gives like electromagnetic or magnetic moment. Do you guys have a, you know, procedure with that?
Yeah, we have a lot of plans. First, just to confirm, so the first deviation we saw was about 20 years ago at Brookhaven.
Wow.
And then they redid the experiment because they were like, well, that's interesting, let's do it again. They moved the whole experiment over to Fermilab in Chicago, and they did it again. And this involves moving a huge magnet. It's like massive. It had to be like on a boat at some points. Did the experiment again, and they announced that's the new news. The result from April is updated. They did everything again. It's much more precise, and they still see the discrepancy. And in fact, it's even bigger. So now they're more confident in it. So what are we going to do to try to understand and explain it? Well, first of all, we got to dampen our expectations, because one possibility is that it doesn't mean anything, is that it's just a mistake. You know, like everybody here is very smart. Everybody's working very hard, but it's easy to make a mistake. And there have been times in the past when they have made mistakes. Like early on, they thought there was a bigger discrepancy than they saw initially because they got a plus sign and they had written it as a minus sign accidentally. These are people. People make mistakes.
Yeah, we do make mistakes.
And people are double checking. But, you know, the theory community doesn't actually even agree on what the number should be. People are talking with a lot of excitement about how the experiment differs from the theoretical prediction by a lot. But there's a different theoretical prediction done by other people using a different method, and they get a number which agrees with the experiment, which says, no, there's no discrepancy. Everything looks like it's just photons and the particles that we know. Now, those theorists are arguing with each other. You're wrong. No, you're wrong. You forgot to account for this. You forgot to account for that. So there's still sort of like one thing to do is just to wait and let the theorists sort this out. Is this real? Or who made the mistake? Or, you know, what's the final answer? And this is a big project. Like it takes millions of computer hours to do these calculations, to consider all the things a photon can do. So it's not easy. But you're right. Another thing that could be is that it could be a new particle. So what can we do? If it's real, if the discrepancy is real, what can we do to understand it? One thing we can do is we could try to see the new particle directly. Like this is a very indirect way. Another way to do it is to see it directly, like at the Large Hadron Collider. So this is exciting because we are about to turn on the collider again after like fixing it and upgrading it, making it better and faster and sleeker. And we're going to run it for like 10 years to really try to find any hints of new particles. So this is great news because it says, hey, we think there's something for you to find. And it's much easier to know what you're dealing with if you find it at the particle collider, because there you're actually making it. It doesn't just exist for like 10 to the minus 23 seconds and then disappear back into the cloud. You make it, it gets created, it turns into stuff. You can see that, you can study it. You can measure the rate at which it happens, just like with the Higgs boson is now something that we're making all the time and studying in detail. So one thing to do is like, well, hope that we see this at the Large Hadron Collider and can study it out the wazoo. That would be great. Even without that, though, you're right that there's theoretical work. Like you were saying, we suspected the Higgs boson existed before we saw it because we looked at patterns and there were things missing. So we can look at this and say, well, what else could explain it? We don't just have to say, we don't know, it's something new. We can come up with an idea that might explain it and explain what we see. And there are ideas like that. For example, there's a guy at Fermilab, a friend of mine named Dan Hooper, and he has an idea for a new force, like you were saying before, a new particle that comes from a new force. So there's the weak force, for example, and it has the particles, the W particles and the Z particles. These are like photons for the weak force. Well, what if there's another weak force that we've never found before? And it has other particles, call it the Z prime, like a new version of the Z boson. So this is like a particle similar to one we've seen in the standard model, but another one. And it could exist. And if it does exist, it would be created by photons in these little exchanges. in these little things that swarm around the muon's magnetic field. So it would explain that. And it would also explain some other things we see in science that we don't quite understand. Like we don't totally understand how fast the universe is expanding. And if this Z prime exists, it might have existed in the very early universe to sort of change how things expanded in the very beginning. And if your listeners have heard about the Hubble tension, this disagreement about how fast the universe is expanding, this would explain that also. So I don't know if this idea is correct, but it's a kind of thing we can do is like, let's look for a story that explains what we see and also makes sense for other reasons, and also maybe explain something else at the same time. And so that's another way to do it, is to try to like find a story that fits, you know, and then find ways to check it. Like if this story is true, how could we tell? What experiment could we do to tell if this story is true rather than some other story? So you need to come up with other experiments, ways to test it.
Okay, yeah, because that's the hard part, because we can have a lot of theories, but if we don't come out with a way to test it, it doesn't work. It's never gonna work.
Yeah.
But
otherwise, it's just a story, right?
Yeah. So I have a pretty interesting question that I always think about, because there's a few things. Like number one, I know we observe these collisions and these movements in the Large Hadron Collider, but we don't actually see pictures, like actual you know, like particle, like a electron is like what, like 10 to the 23 or something like that. Those are things that are way too small. So how do we see them, you know, the way we see them, number one. Number two, like a particle like the muon, that, you know, like it's like a lot of energy. How do we create a particle like that? Is it with collisions too?
Yeah, great question. So how do we see these particles? Well, you're right, they're tiny, but they have energy and they have charge, and we can use their properties to make them reveal where they are. And so we have these layers of detectors, and when a particle passes through the detector, it will leave a little trace. So for example, one thing you can do, and you can build this yourself at home, is like a little cloud chamber. You build a little box and you fill it with vapor, like water vapor. Then as a particle passes through it, it will make little drops. A charged particle will make little drops appear. And so you get like a little trace of a particle. If you Google cloud chamber, you can learn like how to build one at home, and you can see muons passing through it. It's pretty awesome.
Wow.
Well, yeah, what we do is basically that. It's fancier. It's like made with electronics, but basically we try to get particles to reveal where they were. So, you know, we have at the Large Hadron Collider, we have collisions of particles, and then something that happens is made there, and then you get this explosion, like electrons and muons and other stuff fly out. And we just try to like see the paths of those particles as they fly out based on these detectors. So it's like taking a picture. You know, we have like layers and layers and layers of detector, and we say, okay, a particle went through here, and then here, and then here, and then here, and we make a path of the particle. So that helps us tell like where the particles went. And then we assemble it all into this 3D picture of this explosion. And then we try to recreate. We say, well, if we had this explosion, what does that mean happened at the core? Sort of like looking at a car accident and figuring out what happened based on, you know, where the glass is on the street and where the wreckage is and that kind of stuff. So that's sort of how we see particles. And there's lots of really cool technology involved. Some of it is like thin layers of silicon technology that we stole from the computing industry. Some of it involves like thick slabs of iron that slow particles down as they move through them. And we want to use iron that's very radioactively quiet. It doesn't have like radioactive impurities. So we like to get iron from old ships. And like a lot of the iron we use in these devices, are from like old Russian battleships pre-World War II, because the iron's just been sitting there and all the radiation is like decayed out of it. It's much better than new metal that has newer impurities. So like old Russian battleships help us see these particles.
Wow, that's so cool. That's so cool.
And then your other question was how you make muons. Right. Muons, they're not easy to like just collect. They are raining down from the sky, but they're sort of difficult to gather. And so to make them, we use another particle collider. Fermilab has a particle collider, and it smashes protons basically into a blob of stuff. And what comes out is a huge spray of random particles. But a lot of those turn into muons. They decay into muons. So then you got to filter it. So you like put some shielding up so that everything else gets blocked, because muons are pretty good at passing through almost everything. So you
because of the energy?
Yeah, they have the energy, and they don't radiate it very much because they have a lot of mass. So the mass helps them like punch through stuff. So you have protons smash into a big target, which creates a big shower of random stuff. Then you have a shield that shields out almost everything but the muons. Then you have a little magnet, which bends away charged particles like muons and keeps other stuff like neutrinos and stuff going the other direction. So you create a big explosion, you filter out the pieces you want, and those are the muons. So that's how you get a beam of muons like we have at Fermilab.
Wow,
it's pretty cool. There's
so
people
brilliant. Oh my God.
Yeah, I know, it's a lot of work. People who
So
do just
brilliant.
that, like create muons.
Wow, it is so brilliant. Like everything have a way to do it. You know, it's crazy. It's crazy. Either we move it with magnets or then we put shields on it. Like you guys think about everything. That's crazy. Like even the detectors, like when we try to detect like the neutrinos coming from the, you know, from Earth or whatever, we know like what element is good to see the traces or
Yeah.
splash of water on it. Like, how brilliant. This is crazy.
It's cool. And one of the things I really like about particle physics is that there is room for all different kinds of people. Like there are people who really like to build particle accelerators, and people who really like to build detectors, and people who really like to do electronics, and people who like to, you know, keep things cold. And my particular areas, I really like data analysis, like getting the data and doing statistics on it and thinking about how to do the calculations and how you know when something is significant and when it's not significant, and how to teach computers to recognize stuff. That's my jam. But particle physics is a big group of people, from people who like to dig tunnels to people who like to operate machines to people who like to do everything. And so we got experts in all kinds of stuff. So you get to learn from all these people. It's really fun.
Man, that's great. We're almost finishing, but I want to ask you a question real quick. Last time we talked, you were involved, you know, in the LHC, you were involved in the findings of a particle, if possible, of the dark matter. This is maybe like a random question, but I don't know if maybe you have to think about it or somebody say anything about it. But you know that particles, they collide, they come into pairs and etc. But could it be by any chance out of like these interactions that are giving like an extra magnetic moment to this muon, maybe a particle that we cannot see? So maybe a particle that can be part of like the dark matter that is around there at all?
Yeah, it is possible that what we're seeing in the muon is evidence of a new particle, and that new particle is dark matter. Wow. Or connected to dark matter. It's possible. Now, it's not that likely because, as we said, photons, the new particle has to interact with photons. And we know that dark matter doesn't interact with photons. So it's probably not dark matter. But we don't know for sure, because it could be that dark matter feels some new kind of force. And it's like a dark electromagnetism, a new like copy of electromagnetism. So it might be that there's a dark photon. And what we could be seeing is not dark matter directly, but the dark photon, which could indirectly interact with the photon. They could, like, you know, talk a little bit. And because what we're looking at is a really small difference. Like if you wrote down the muon's magnetic moment as measured and as predicted, you know, the numbers like agree to 12 decimal places, and then there's a difference. So it's a very subtle difference. So even a small effect could explain it. So yeah, it's possible that this is a hint of dark matter. And it's exciting because we know dark matter is a thing, right? Of all the possible explanations for what this could be, we know dark matter is a thing that's unexplained. And that makes it exciting to look for, because it's, you know, most of the universe, and we want to understand it. I'm not sure about it here, but it's a possibility.
Yeah. Wow, that's great. That's great. Daniel, I know we don't have a lot of time today, but I think that we have it pretty clear. I think like the main thing with the muon right now is like we find a little bit of different, like 12 decimal numbers down. So it's not a lot, but it's significant enough. So we realized like it was something weird happening. So, you know, for me to kind of put it together, it's like we have those photons going around the muon, and it kind of shape whatever weight of the magnetic field that the muon is supposed to move or react. So for some reason, it's hitting a little higher, you know, like have a little bit more of magnetic moment that we assumed before. So that's pretty much what's going on now, but we for sure don't know completely what is creating that. That's pretty much what the news said.
Yeah, that's exactly right. You're basically a particle physicist now.
Hey.
Or at least you are particularly clever.
Oh, thank you. You are so nice with me. Daniel, this has been a huge pleasure. I'm crazy to talk to you guys again, like you and Daniel at some point, you together. Thank you a lot. Thanks, you know, because you always said yes. Like since I was nobody, still I'm not, but I mean, at least you know, more people listen to me now. But
Well,
you always said yes.
Thank you for encouraging curiosity. I mean, I love to talk to you because we are of the same mind. You know, curiosity is the thing that drives joy and wonder in the world. And everybody is a scientist if you're curious about the way the world works. You don't need a PhD in particle physics. You just have to wonder about the world. And then that's all that science is people wondering.
That's great. That's great. So to end this today, I usually give a recommendation. I already talked about your book at the beginning of the podcast, but usually I ask, you know, I usually recommend a book, but I ask you don't have to recommend a book, but I know you're a pretty science fiction guy and you read a lot of them. So it could be a science book or a science fiction if you want to recommend something for my peeps today.
Yeah, there's a great book about quantum mechanics called Helgoland. It's just coming out by Carlo Rovelli, and it's a new idea about quantum mechanics. Just read it, really fascinating. The guy's a great writer. It's like poetry. Plus, there's some really cool ideas in there about what it means when you measure a particle and what that even means. And so it's a lot of fun. I totally recommend it. It's called Helgoland by Carlo Rovelli.
Oh, that's good. Then since you recommend something from Carlo Rovelli, then I'm going to recommend another thing from Carlo Rovelli.
Yes.
And it's called Reality is Not What It Seems, The Journey to Quantum Gravity. And that's from Carlo Rovelli too. So my other book, Curiosidad Científica Podcast, El Universo en Arroz con Habichuela. Do you know what that means? El Universo en Arroz con Habichuela.
A universe with rice and something?
And beans, yeah.
Rice and beans.
The universe in rice and beans. So it's
like beans is frijoles.
Yeah, because in South America it's frijoles. We like Caribbean, we call it habichuela. So yeah, everything is with rice and beans. In English, yeah, the translation is rice and beans. So that's the universe in rice and beans. That's my book. That is like way basic physics science for you guys, and you can find that in Amazon or whatever you want to look for it. So Daniel, thanks a lot. Thanks. Where can we find you? Because I know you have some podcast that is pretty big around there. What's going on?
You can just Google me, Google Daniel Whiteson, or go to our website, danielandjorge.com, and check us out everywhere podcasts are found.
Thanks, Daniel. For all of you guys, thank you for listening, and subscribe and share all this so we can keep it up. So thank you. Bye bye.
Y para ustedes, esto es curiosidad científica.